Okay, so we're going to move on now to a discussion of electrolysis. And as you can see on the screen, the definition of electrolysis is shown. It is the process where you use electrical energy to cause a non-spontaneous chemical reaction to occur. So that is different from what we saw earlier when we were looking at galvanic cells, where a chemical reaction, which is spontaneous, is used to produce an electric current. So that's a difference between what we saw then and what we're looking at now in terms of electrolysis. And you can have the electrolysis of the molten form of the ionic compound as shown in this diagram right here. This is basically the setup for the electrolysis of sodium chloride. And what will happen is that it will basically cause these half reactions to take place, where the chloride ions will be oxidized to form the chlorine gas. So you can see chlorine gas being formed here. And then the sodium will be reduced by the electrons produced by the chloride ions to form the sodium metal. And you can see the liquid sodium being produced here. All right. So that's basically what happens. Now, what we said before in terms of the electrodes and what occurs at the electrodes is also true here. Oxidation always takes place at the anode. So this reaction here will take place at the anode, which is shown here in this setup, or shown over here in this setup. And reduction will take place at the cathode, which is shown here and here in the setup over here, and shown here in the case of the sodium chloride in this setup over here. All right. So that's basically what happens in electrolysis. You're using an electric current to drive a non-spontaneous reaction. Now, what you're seeing here on the screen is the electrolysis of water. Now, you might be wondering why we have dilute sulfuric acid solution here. Well, the reason is that the presence of dilute sulfuric acid or sulfuric acid will basically increase the rate of the reaction because it's easier for the electrolysis to take place when the solution is containing ions. In any case, what happens here in this reaction or in this setup is the electrolysis of water, where at the anode where oxidation takes place, the water will undergo oxidation to form oxygen gas as well as H+ ions. And then over here, in the case of the cathode, reduction takes place, where the electrons will be reducing the H+ ions to form H2 gas. So therefore, when you add these two equations together, basically you're going to get the overall reaction where H2O is being broken down into oxygen gas and hydrogen gas in a 2-to-1 ratio. And this is showing you basically a natural setup where oxygen is collected and H2 is collected in this tube. And as you can see, it's a 2-to-1 ratio when that occurs, which reflects the 2-to-1 ratio according to the half equations shown here. So that's basically what happens in the case of the electrolysis of water. Now, let's look at some quantitative aspects of this process. Firstly, I need to define what we mean by charge. The amount of charge is basically equal to the current multiplied by the time. All right. And also, we met this before, but it will become more important here. 1 mole of electrons carry a certain amount of charge, and that charge is 96500 coulombs. And this is known as Faraday's constant. All right. So 1 mole of electrons carries this amount of charge, and a unit of charge, coulomb, is equal to 1 ampere multiplied by 1 second. So we can apply what we have learned. Well, before we get to this example, so typically problems involving electrolysis usually starts with somehow determining the charge, and this is where the current multiplied by time comes in, and we convert that charge. That charge will be expressed in coulombs, and then we can divide by the Faraday constant to get the number of moles of electrons, and then we look at the half equation to determine the moles of a particular substance being oxidized or reduced. And of course, we can go from there to determine grams of a product using the molar mass, or we can use the ideal gas equation, or in some cases the molar volume, to determine liters of a gas if a gas is involved. All right. Or we can go the other way as well, right? It all depends on what you're given in the question and what the question is asking for. So let's look at this example. This question says, how much calcium will be produced in an electrolytic cell of molten calcium chloride if a current of 0.452 amperes is passed through the cell for 1.5 hours? So let's look at the reaction that takes place. At the anode, oxidation will take place where the chloride will be oxidized to form chlorine. At the cathode, calcium will be reduced to form the calcium solid according to this half equation. And the net equation, when you add these two, of course, will be this reaction right here. Now, let me just say that for this particular question, you really only need this equation right here, right? This half equation. Because this equation tells you basically how much calcium will be produced per 2 moles of electrons, right? So the way we'd go about solving this is that we determine firstly the charge. So therefore we multiply the current, which is 0.452, measured in amperes, which is the same thing as coulombs over seconds, and we multiply it by the time. So the time would have to be converted to seconds. So we start with the 1.5 hours times 3600 seconds per hour, and then we multiply that by the mole ratio, or not the mole ratio, but the conversion factor, which represents the Faraday constant. So we have 1 mole of electrons above, the Faraday constant below, and then the next conversion factor is where the mole ratio comes in between the number of moles of electrons and the moles of calcium. So if you set it up this way, you'll see the units canceling out like so for the hours. The seconds will cancel out, the coulombs will cancel out, the electrons will cancel out, the moles of electron, that is, and the only unit remaining after all this would be the moles of calcium. And when you work this out on your calculator, you're going to get 0.0126 moles. But of course, it depends on how you want to express the amount of calcium. You could leave it like this, or you could take this further and convert it to grams. And of course, you know how to do that. Use the molar mass and multiply the molar mass by the moles, and that gives you the grams. All right? So that's basically how you'll do a problem of this type. Okay, so that's basically it for this chapter. The only thing I want to show you here is an example of an electrochemical reaction that takes place when dental filling is corroded. I can tell you that I've had the personal experience of having that happening. Dental filling, in some cases, back in the 90s, I know for sure, or I should say in the 80s when I had it done, used to be done with an amalgam of tin, and this is the tin amalgam right here, and it will undergo over time oxidation. So the tin that's a part of the amalgam here will be converted to tin ions. So you have oxidation taking place, and at the same time, the electrons produced as a result of the oxidation of the tin will be used to basically reduce oxygen in the presence of H+ ions, and you're going to get water being formed. So water will be a byproduct of that reaction. All right, so that's just one simple example, and we can look at the quantitative measurements associated with these reactions as given by the voltages over here. Okay, so that's it for this chapter. So the next chapter will be the chapter dealing with nuclear chemistry.